Hello students. In this video lecture, we are going to discuss about mathematical expectation. Mathematical expectation of. So as we are discussing the two-dimensional random variable, so we'll discuss the mathematical expectation of two-dimensional random variable. Slightly two-dimensional random variable, it is in the form of function here. So that's a mathematical expectation of a function of bivariate distribution. Function of bivariate distribution, right? So already in your lower classes or lower semesters, you studied the what we mean by mathematical expectation, right? So mathematical expectation is denoted by expected value of x. If x is a random variable, that is denoted by e of x. Usually it is known as average or mean, right? Average or mean or expected value, right? So expected value of x is nothing but we have a certain formula to calculate expected value of x. That is summation I running from 1 to n xi into probability of xi, right? So for all I running from 1 to n, when it is if x is discrete case. And we have already studied integration minus infinity to infinity x into f of x dx, right? If x is continuous case, right? So this is already studied in our lower classes, means what I think now you are in third ones, you studied in second semester, right? So these are mathematical expectation. But the thing is, my question is, so how to find out mathematical expectation of x plus y, or how to find out mathematical expectation of x square, or how to find out mathematical expectation of x into y. Here we have two variables, one is x and one is y. Here only one variable, but it is in the form of some function, that is x square, so x square. So here two random variables multiplied x into y, like that. If we can define one more function, that is expected value of x square plus y. So how to find out all these values, right? For such we have the concept of, that is mathematical expectation of a function in a bivariate distribution, right? So here to discuss the mathematical expectation of a function in a bivariate case, again we have two cases. One is discrete case and one is continuous case. So first one, discrete case, and as usual we have one more, that is continuous case, right? So when we consider the definition regarding definition, suppose we consider, right? So let x and y be the, let x and y be a two-dimensional two dimensional discrete random variables, discrete random variables with probability density function, with probability distribution here, not density, probability distribution Pij for all I running from 1 to m and j running from 1 to n. Then if g of xy, then if g of xy be a real valued function, be a real valued function, then expected value of sorry, not g, expected value of this xy, expected value of then expected value of g of x comma y is given by double summation double summation I running from 1 to m and j running from 1 to n g of xy, I mean g of x comma y into pij, right? So this is nothing but the discrete case mathematical expectation of a function in bivariate distribution definition, right? So just to check one more time, let x and y be two-dimensional discrete random variables with probability density function Pij, where I running from 1 to m and j running from 1 to n. Then if g of xy be a real valued function, then expected value of g of xy is given by double summation g x comma y into Pij. Say for example, if our g of x comma y may be x plus y, right? So then expected value of x plus y is given by double summation I running from 1 to m 1 to m and j running from 1 to n xi plus xi plus yj into pij, right? So in this way we can find out, say for example, if this is for example, if g of x comma y equal to x square y, then expected value of x square y is nothing but double summation I running from 1 to m and j running from 1 to n x square I into ij into pij, right? So we can calculate, I mean we can observe one more example. Say for example, if g of x comma y equal to only xy, then expected value of xy is nothing but double summation I running from 1 to m, j running from 1 to n, xi yj into pij, right? So in this way we can uh, calculate mathematical expectation of a function in bivariate case, right? So better is we'll discuss first bivariate case, later we'll go for continuous case, right? So first we'll discuss entire the concept of bivariate case. So this is what the definition of the expected value of x for the bivariate case. Now we'll see one example how to calculate the expected values. Example, for the for the following probability distribution, for the following probability distribution of x comma y, compute first one, expected value of 2x plus 3y, second, expected value of x square into y. So they given x and y values they given. So here x and y. So y values are 1, 2, 3. Then x values are -1, 0, then 1. So these values are given 0.15, 0.1, 0.2, 0.05, 0.05, 0.05, here 0.15, 0.20, 0.05. So this is the given distribution, and we need to calculate the expected value of 2x plus 3y and expected value of x square into y, right? For this, in our case, we know that for that discrete case, mathematical expectation is given by, sorry, not expected, so not summation. Expected value of g of xy is equal to double summation I running from 1 to m, j running from 1 to n, g of xi comma yj into bij, right? So here instead of xy, what we have? First one, expected of 2x plus 3y. Here g of xy is nothing but 2x plus 3y. So the formula double summation I running from 1 to m, j running from 1 to n. Instead of g of xy, what we have? 2x plus 3y we have. Then pij. Pij is nothing but probability at 1 comma 2, probability at 0 comma 1, like that, according to this scenario, right? So now what we'll do, we'll fix the x value and we'll go on through y values. Next we fix x values, go on y values, fix x values, go on y values. Say for example 2 into minus 1, that is minus 1 is fixed, plus 3 into first y value is 1, 1, then minus 1 comma 1, probability is, for this entire thing, probability is 0.15, right? Plus now minus 1 and 2, so 2 into minus 1 plus 3 into 2, for this 0.01, plus minus 1 is fixed, we need to go for 3, so 2 into minus 1 plus 3 into 3, for this probability is 0.2, plus, okay, first minus 1 series is completed with various values of x. Now we'll fix this 0, then we go for the various values of y, right? So 2 into 0 plus here 3 into 1 into this value is 0.05, plus 2 into 0 plus 3 into 2, the value is 0.05, plus 2 into 0 plus 3 into 3 into 0.05. So with respect to x equal to 0, all the values of y are completed. Now, plus with respect to x equal to 1, we go for all the values of y. So 2x, 2 into 1 plus 3 into 1 with probability 0.15, plus 2 into 1 plus 3 into 2 with probability 0.2, plus 2 into 1 plus 3 into 3 with probability 0.05, right? So here you can multiply and add, right? So the final answer you will get 5.75. 5.75 is nothing but it is equal to expected value of 2x plus 3y, right? So in this way we can get the expected value of any function. So next case, that is second example, I mean first in first example only, second sub question, expected value of x square we need, right? So this is nothing but the same formula, I running from 1 to m, j running from 1 to n, g square, sorry, x square y pi j. So here first we'll fix the x value, that is minus 1, and we'll go on changing the y values, minus 1 square into 1 with a probability 0.15, plus x is -1, its square, and y is 2 with the probability 0.1 plus x is fixed multiplied by y with the probability 0.2 plus, right, next 0 square 1 0.05 because x is 0 and y value go on changing. So 0 square y value is 2, then 0.05 plus 0 square y value is 3 into 0.05 plus next x value is 1, that is fixed, then y value go on changing. So 0 square into 1 into 0.15 plus 1 square into 2 into 0.2 plus 1 square into 3 into 0.05, right? After simplification, you will get the 1.65. So this is what expected value of x square y. This is what expected value of x square y. So in this way, we can get the values of expected value of any function. We can go through this small example with this formula, right? Now, related to this expected value of x only for discrete case, we have some theorems. So now we are going to state and prove those theorems, right? Theorem number one. Theorem one. This theorem is also called as addition theorem of expectation. Addition theorem of expectation, right? It is also called as this one. So now we will discuss the statement of that theorem, right? So x and y, let x and y be two discrete random variables, then expected value of x plus y is equal to expected value of x plus expected value of y. So we need to prove this theorem. I already told you this theorem is called addition theorem of expectation. So what that theorem says, let x and y are any two discrete random variables, then expected value of x plus y is equal to their individual sum, that is expected value of x and expected value of y, right? So proof, let us consider Pij be the let's consider Pij be the probability of x comma y for all I running from 1 to m and j running from 1 to n. So consider this LHS part, that is x plus y. So by definition, double summation I running from 1 to m, j running from 1 to n, xi plus yj into pij. This is what by definition, right? Now double summation as it is, I running from 1 to m and j running from 1 to n, right? So here I will multiply this pij inside xi into pij plus yj into pij, right? So what I did multiplication of this pi into inside. So now I will apply the summation into the bracket, right? So I will apply the summation inside the bracket. So now what we'll get? We'll get double summation I running from 1 to m, j running from 1 to n. Xi into Pij plus as it is double summation I running from 1 to m, j running from 1 to n, yj, pij. Right. Now I will operate this summation into inside. So I running from 1 to m means it is applicable here. That is like this summation I running from 1 to m xi and summation j running from 1 to n pi comma and pij plus here j, because here y is respective variable j, so j running from 1 to n yj summation I running from 1 to m pij, right? So now summation I running from 1 to m xi, this is nothing but capital P dot, pi dot, right? So pi dot is nothing but summation j running from 1 to n pij. This is nothing but what? Marginal distribution of x. This is what? Marginal distribution of x, right? Definition exists, right? Summation of the bivariate probability over the opposite range. Suppose I need marginal distribution of y, take range on j. Suppose I need marginal distribution of y, take range on j. X means j, y means I, like that. Plus summation j running from 1 to n yj capital P dot j. So capital P dot j is nothing but summation I running from 1 to m pij. So capital dot j is nothing but marginal distribution of y, right? So this is nothing but our definition exists. This is what expected value of x plus this is what expected value of x. Already here we have, that is expected value of x plus y is equal to expected value of x plus expected value of y, right? So this is what the proof of addition theorem of the uh, expectation, right? So here we can extend this theorem for any number of observations. Say for example, suppose I need expected value of x plus y, I can take expected value of x plus expected value of y. Suppose I need expected value of x plus y plus z, one more random variable. This is equal to expected value of x plus expected value of y plus expected value of z, right? So in generalization, right? If x1, x2, x3, and so on up to xn are n random variables, are n random variables, then expected value of x1 plus x2 plus x3 and so on up to plus xn is equal to sum of their individual expectation. That is what expected value of x plus expected value of 2, expected value of x3 and so on up to plus expected value of xn, right? So this is what, this is nothing but a generalization form of addition theorem of expectation. This is what additional theorem of expectation, right? So I hope it is clear theorem and proof. So now we have the multiplication theorem of, just a second. Now we have theorem number 2, that is theorem 2, multiplication theorem of expectation. Now, same as it is, we have statement. Let x and y be two independent, discrete, random variables. Then expected value of xy is equal to expected value of x into expected value of y. So this is what addition theorem of this is what multiplication theorem of expectation, right? So here the important thing is sorry, x and y be the two independent, x and y be the two independent, right? But in previous case, where in addition theorem of expectation, x and y be any two discrete random variables, but here we required any two independent only, right? Otherwise, this theorem is not suitable for dependent variables. It is only true, or it is only suitable for independent variables. So what that theorem says, expected value of xy is equal to expected value of x into expected value of y. So now we are going to prove this theorem. Proof. Let us consider the format of the theorem. Proving the theorem is same. Let us consider Pij be the probability of x comma y for all I running from 1 to m and j running from 1 to n. Then capital Pi dot is nothing but summation over j running from 1 to n Pij, and capital P dot j is nothing but summation I running from 1 to m Pij are marginal probabilities of x and y respectively. Marginal probabilities of x and y respectively, right? So then what we'll do, then we'll consider the same LHS part, that is consider expected value of xy is equal to double summation I running from 1 to m, j running from 1 to n, xi yj into pij. So now here expected value of xy is equal to summation I running from 1 to m, j running from 1 to n, j running from 1 to n, then xi yj can be written as individual probabilities like capital Pi dot and capital dot P dot j. Why? Because x and y are independent variables. We know that independent variable is nothing but f of xy is equal to f of x into f of y. This is the concept here. Here two-dimensional random distribution is divided into individual, right? So these are not marginal. So joint probability density or joint probability mass function is divided into marginal distribution because of this concept. Now expected value of x into y is equal to summation I running from 1 to m. So xi pi dot into summation j running from 1 to n yj p dot j. So expected value of xy is nothing but this entire thing is expected value of x into this entire thing is expected value of y, right? So this is what proved. So likewise, uh, generally, right? Suppose we need expected value of xy. So here x expected value of x into expected value of y. If and only if x and y are independent. If they are dependent, this theorem is not good. This theorem is not holds good. Second, expected value of x, y, z. Suppose I need this expected value of x into expected value of y into expected value of z, in the sense that x, y, z, all three should be independent variables. So generally, the general format, right? If x1, x2, x3, and so on up to xn are independent n random variables, independent n random variables, then expected value of x1 into x2 into x3 into x4 into and so on up to into xn is nothing but product of their individual expectation. That is nothing but x1 into expected value of x2 into expected value of x3 into and so on up to into expected value of x, right? So this is called multiplication theorem of the expectation, or this last format is called generalization of multiplication theorem. Now with respect to this theorem, we have one more point, right? So converse of the above theorem is not holds good. It means that converse may not be true. Either it may be true or it may not be true. Then what is the converse, right? So what theorem says, what theorem says here, let x and y are independent variables, then expected value of x y is equal to expected value of x into expected value of y, right? So converse of this theorem is not true. That is, if expected value of xy is equal to 0, then we can't say x and y are independent, right? Converse theorem says that if expected value of xy is equal to 0, then x and y may not be may not be independent, right? If expected value of xy is equal to 0, even though we can't say that x and y are dependent or independent, right? So we can't say. But if in case x and y are independent random variables, then we say that expected value of xy is equal to expected value of x into expected value of y, right? So for this third point, sorry, for this fourth point, we have one example. So now we'll solve that example here. Okay, we'll solve that example here. Let xy have the let xy have the following oh, joint the joint PMF, right? So here x and y minus 1 0, 1. They given their marginal probabilities also here. So 0, 1, 2. Even though they given marginal probabilities of x as well as y. Right? So here 0, 1 by 6, 0. Sum of this is 1 by 6. 0 plus 1 by 6 plus 0, that is 1 by 6. Then 1 by 6, 0, 1 by 6. 1 by 6 plus 1 by 6, 2 by 6, that is 1 by 3. Then 0, 1 by 2, 0, 0, 1 by 2, I mean 0 plus 1 by 2 plus 0, that is 1 by 2. Then 0 plus 1 by 6 plus 0, 1 by 6. Here 1 by 6 plus 1 by 2, that is 2 by 3. This is 1 by 6 and overall is 1. Right. So just it is a counter example for that last point. So now what we'll do, now we'll find out expected value of xy. So we know that formula summation, I mean double summation, I running from 1 to m, j running from 1 to n, right? So xy into p I j. For all, I can take the values with the 1 to m and j can take values with 1 to n. So now, expected value of xy, x into y, then see here. First we'll fix the x. So 0, now 0 into minus 1 into this 0. Next, plus summation is there, plus 0 is fixed, minus 1 is completed. 0 is fixed, I'll go with 0. So 0 into 0, 1 by 6. 0 is fixed, now take 1 plus 0, 1, 0 plus now 1 minus 1, right? So 1 minus 1 with probability 1 by 6 plus 1 fixed with 0, that is 1, 0, 0 plus 1 is fixed with 1, that is 1, 1, 1 by 6 plus now we'll fix 2, change the values of y. 2 into minus 1 into 0 plus 2 into 0 into 1 by 2 plus 2 into 0 into 1, right? So here expected value of xy is equal to, after solving this on, we'll get the 0, right? So here what? Expected value of xy is equal to 0, but x and y are not independent. X and y are not independent. This is only last point. If x and y are dependent, expected xy is equal to expected value of x into y, otherwise not. You can cross check here, right? So here expected value of x, that is nothing but summation xi into pi dot I running from 1 to m, right? So this is nothing but 0 into 1 by 6 plus 1 into 1 by 3, that is 1 by 3, 1 into 1 by 3. Next 2 into 1 by 2, that is 0 plus 1 by 3 plus 1. 0 plus 1 by 3 plus 1, that is 4 by 3. Next, expected value of y, summation j running from 1 to n, yj p dot j, that is minus 1 into 1 by 6 plus 0 into 2 by 3 plus 1 into 1 by 6. This is 0, right? So here expected value of xy is also 0. Expected value of x into expected value of y equal to 0. Hence we say that expected value of xy is equal to expected value of x into expected value of y. But x and y are independent, right? Sorry, not independent. But x and y are not independent. Why? Just see here. For 1 and minus 1, we have common probability. For 0 and 0, we have common probability. For 1 and 1, we have common probabilities. right? So even though this exists, but these are not independent. But if they are x and y are dependent, this exists always. But converse, if it is exist, either x and y are either dependent or independent, we can't say. This is what the counter example for that last case. So now we'll discuss the continuous case. Right, up to here, whatever we discussed, that is a discrete case. So now we have continuous case, that is continuous case definition. Continuous case definition. So now we'll see what definition states or what definition tells. If x and y, if x and y is a bivariate, random variables, bivariate random variables with joint PDF f of xy and g of xy is a function in x and y, is a function in x and y, then expectation of g of x comma y is denoted by, then expected value of g of xy is denoted by expected value of g of xy is equal to double integration minus infinity to infinity g of x comma y into f of x comma y dx dy, provided that double integral should be exist. It means that double integration should be exist, right? So this is a simple case, that is continuous case, where expectation value, I mean bivariate expectation we can find here, right? So now we have examples. And before example, similarly, we have the same here also addition theorem and multiplication theorem are there. Now we'll discuss multiplication as well as addition theorem. First, in that, we'll discuss the addition theorem of expectation whenever random variables are continuous case, right? So theorem, if xy, I mean x comma y is a bivariate random variables, sorry, bivariate random variables with joint PDF f of x comma y, then expected value of xy is equal to expected value of x into expected value of y. It's very simple. We need to prove this. Usually such kind of questions will ask for 4 marks in your semester and exams. So proof by the definition, by the definition, what our definition says, expected value of g of xy is equal to double integration minus infinity to infinity g of xy into f of xy dx dy. Instead of g of xy, what we have here? Here g of xy is nothing but x plus y. That's it, right? So double integration minus infinity to plus infinity x plus y f of xy dx dy. This is what our definition says, right? So expected value of x plus y is nothing but integration minus infinity to infinity, I mean double integration minus infinity to infinity x f of xy dx dy plus integration minus infinity to plus infinity y f of y dx dy. So expected value of x plus y is equal to minus infinity to infinity. I will take x common here, x, then one more integration minus infinity to infinity f of xy dy dx. I will write like this, plus integration minus infinity to infinity. I will take y common, integration minus infinity to infinity f of xy dx and dy. Correct? So integration of x plus y, integration minus infinity to infinity as it is, x is also as it is. So this is nothing but what? Again, marginal distribution of x. It is integration minus, sorry, integration f of xy dy is nothing but definition of marginal distribution of x. That is f of x dx as it is, plus as it is, minus infinity to infinity y. This is a marginal distribution of y, that is f of y, then dy as it is, right? So here, this is nothing but expected value of x. So expected value of x plus y, right, is equal to expected value of x plus expected value of y, right? So very simple proof of this. Some here also some we have some remarks for this. Remarks, right? In this case, first one, if a equal to 1 and b equal to minus 1, then expected value of ax plus by is equal to what happened here? Expected value of ax plus expected value of by. So what is a equal to 1 and b equal to minus 1. So expected value of x, sorry, not plus, it will be minus. Expected value of minus expected value of x minus y is equal to expected value of a is 1 into x minus expected value of y here, right? So it is also true in generally. Now we can extend into uh, n number of or k number of observations or random variables, right? If x1 x2 so on up to xn are n random variables, are n random variables, then that is addition theorem, x1 plus x2 and so on up to plus xn is equal to expected value of x1 plus expected value of x2 plus and so on up to expected value of xn also we can write. So very simple proof. This is what the addition theorem of uh, expectation whenever continuous case, right? So now we'll go to the next theorem, that is multiplication theorem of expectation for the continuous case, right? So theorem, if x and y is a a bivariate bivariate random variables with joint PDF f of x comma y and x comma y are independently independently distributed, then expected value of xy is equal to expected value of x into expected value of y. So we can prove this theorem similarly, same. All four theorems are very simple, right? So no need to take any tension. Here, proof. If you thorough with the basic concepts, you can solve easily. Again, by the definition, by the definition. What definition says? Expected value of xy is equal to double integration minus infinity to infinity xy f of x comma y dx dy. Right? So here what they mentioned, since what they mentioned, x and y are independent. Since x and y are independently distributed, it means that what? X and y are independent. When we say independent, any two random variables are independent. F of xy is equal to f of x into f of y. When this exists, then only say that those are independent, right? So now they only told they are independent, means minus infinity to infinity, right? So xy independent. So instead of x comma y, we can write f of x into f of y. So dx dy, right? So further xy is equal to, I will write minus infinity to infinity f of x dx into minus infinity to infinity y f of y dy. So this is f of xy is equal to, this is what expected value of x definition or formula. This is what expected value of y formula, right? So this is the proof, right? So it's a very simple proof for discrete as well as continuous case. Now we'll solve mm, some examples. We'll solve some examples for the uh, finding expectations of bivariate case for continuous. Example, suppose xy is, sorry, suppose xy is a bivariate random variables with PDF f of xy is equal to xy. The range of x is given, that is 0 to 1, and range of y is also given, that is 0 to 1. Then find first one, expected value of x plus y. Second one, expected value of xy. We need to find these two. It's very simple. First one, what they given here? Given that f of xy equal to x into y, the range of x is 0 to 1 and the range of y is also 0 to 1. So now what we need? Expected value of x plus y. This is minus infinity to plus infinity x plus y f of xy dx dy, right? So now here minus infinity means not minus infinity, it should be lower limit, and plus infinity means what here? Upper limit. So lower limit is 0 to 1 for both case, and upper limit, I mean limits are 0 to 1. X plus y xy dx dy, f of x is nothing but dx. So expected value of x plus y is equal to integration 0 to 1, integration 0 to 1 x plus y xy dx. Now I will take dy. So 0 to 1, we'll solve the integration here. Before integration, first I think we'll multiply, that is better, easy. 0 to 1, x into xy dx plus integration 0 to 1 y xy dx, whole integration dy. So expected value of x plus y, integration 0 to 1, open bracket here as it is. So integration 0 to 1 x square y dx plus integration 0 to 1 x y square dx, whole integration dy here. X as it is, then y into y, that is y square, right? So now what we'll do, we'll do the integration, that is equal to 0 to 1 integration y into x cube by 3, 0 to 1, plus y square x square by 2, 0 to 1 dy. Integration 0 to 1, it is y by 3. After integration, it is y square by 2 dy. So integration 0 to 1 y by 3 dy plus 1 by 2 common, integration 0 to 1 square dy. So 1 by 3 by 2, 0 to 1, 1 by 2, integration of y square, square is y cube by 3, 0 to 1. It is 1 by 6 plus 1 by 6. The answer is 2 by 6 or 1 by 3. So this is what x plus y, right? So in this way, we can find out the expected value of x plus y. Then second sub problem here, that is expected value of xy. The same formula, integration minus infinity to infinity xy f of x comma y dx dy. Integration xy 0 to 1, limits are mentioned in 0 to 1, xy, f of x is also xy, so dx dy. So integration 0 to 1, integration 0 to 1, this is x square y square dx dy, right? So 0 to 1, 0 to 1 x square y square dx dy, right? So x square y square dx into dy. This is 0 to 1. First do integration for x. So y square is constant. X square integration is x cube by 3, 0 to 1 dy here. So 0 to 1 y square by 3, 0 to 1 y square by 3 dy. So 1 by 3 common, integration of y square is y cube by 3, 0 to 1. This is nothing but 1 by 3 into 1 by 3. The answer is 1 by 9. So in this way, we can find out the values. I mean, we can solve the examples for the expectation of bivariate uh, random variables from continuous case. Now we have one more example. Example, let x and y, let x and y be continuous random variable, be continuous random variables with joint density function. They mention the function f of xy equal to 2 if range of x, sorry, first range of y they mentioned, range of y is 0 less than y less than 1 minus x, and they mention range of x also 0 less than 1. Then find expected value of xy, right? So we very simple as usual, just to apply the answer. What we need? We need expected value of xy, right? So expected value of xy is nothing but integration minus infinity to infinity xy f of x comma y dx dy. This is the formula. So integration, I mean expected value of xy, integration minus infinity to infinity, sorry, instead of here minus infinity to infinity, they mention some limits. First here 0 to 1, and one more limit is 0 to 1 minus x, right? So here xy f of x is 2, so 2xy dx dy, right? So 2 is out of the integration, so we'll take outside. Now 0 to 1, right? Open bracket. So here 0 to 1 minus x, xy, because 2 is already took outside. Now dy, because it is limit of y, so dy into dx, right? So expected value of xy 2 as it is, integration 0 to 1. I will take x common here because x is independent of variable. So we'll take x common. Now what do we have? Integration 0 to 1 minus x y dy dx, then we'll close the bracket here, right? Oh shit, slides are right. So up to here I can up to here will clear. So now just a bit, right? Now expected value of xy is equal to 2 into bracket. So 0 to 1 x as it is. So integration of y is y square by 2 with the limits. And then as usual dx we have. This is equal to 2 into 0 to 1 x by 2, then y square is 1 minus x whole square, right? So this is what dx, we need to solve this integration. So now 2, so this 2 will be outside the integration sign because it is independent of variable. So 2 by 2 integration 0 to 1 x into 1 minus x whole square dx. So 2 by 2 get cancelled. So what, nothing means 1. 0 to 1, I will okay, I will apply the a minus b whole square formula, x into a square. So a minus b whole square equal to a square plus b square minus 2ab. So a square is 1 square plus x square minus 2 into 1 into x, right, into dx. 0 to 1 x plus x cube minus 2x square dx, right? So x plus x cube minus 2x square dx. So for this apply the integration, that is 0 to 1 x dx plus 0 to 1 x cube dx minus 2 0 to 1 x square dx. So x square by 2, 0 to 1, this integration, plus x power by 4, 0 to 1, this integration, minus 2 as it is, x square derivation, integration x cube by 3, 0 to 1, right? So here 1 by 2 plus 1 by 4 minus 2 by 3, 1 by 2 plus 1 by 4 minus 2 by 3. So this is nothing but 6 by 8 minus 2 by 3. You can solve here. Then 18 minus 16 by 24, that is 2 by 24, or the answer is 1 by 12. 1 by 12, right? So in this way, we can solve several examples with the help of continuous case, right? So this is what the concept of mathematical expectations. This is what concept of mathematical expectation in case of bivariate or two-dimensional random variables. I hope it is clear. If you have any doubt, you can ask freely.